Good evening, all. Welcome to week 8 live session of the Fundamentals of Convective Heat Transfer course. We'll wait for a couple of more seconds for a few more students to join and then we'll get started. Hi, good evening. Good evening. Okay, then I guess we'll get started. I hope my screen is visible, right? Yeah. So since I cannot see your screen, if you have any queries, please unmute yourself. So basically the contents for this week are, we started out with natural convection in this week. In natural convection, we'll start out with some assumptions. The main approximation is the Business approximation, followed by scaling analysis and estimation of Nusselt number for different cases of Prandtl number. And then the lecture videos actually covers about non-dimensionalizing the governing equations, and then the most important number called Richardson number will be discussed. Subsequently, equations are derived for constant wall temperature and solution is also presented in the lecture videos. Even uniform wall heat flux scenario is also discussed, not in that great detail, but the solutions are presented in the lecture videos. So I hope you have already gone through the lecture videos. Are there any specific queries you have in these in the lectures? Okay, if you do not have any specific queries, then maybe I'll quickly give a summary of some of the important concepts that are required, and then we'll discuss the 4 different class of problems. Essentially, all of these problems in this will deal with either determining the heat transfer coefficient or the surface temperature. So the first 2 problems we'll discuss for 2 different boundary conditions, and then we'll understand how much the difference is between the heat transfer coefficient for free versus forced convection in one problem, and finally we will actually solve for velocities. Like up until now, all these problems are on heat transfer and temperature. So I've just taken one problem wherein velocity is also taken into account. So before proceeding, so how familiar are you with programming? If not, then maybe I'll give a brief intro of what is required also, so that the equations are presented. So in order to be able to solve the equations, little bit of programming is required. Now with LLMs, that should be fairly easy. Okay, let us get started then. So the major assumptions that we'll be considering in natural convective problems are to study laminar and 2D flow, and viscous dissipation terms are neglected. This we have discussed even in the last week, where viscous dissipation is accounted is basically when you have high speed flows, and we are assuming that the boundary layer approximation is valid, such that the value of this delta is very small compared to the other dimensions. So if the plate is around 1 meter, then delta will be in the order of millimeters. The temperature difference between the plate and the fluid is small enough so that we can still assume constant properties of the fluid, except for one location, except in the momentum equation. That is where the driving force will actually come into picture. So that's the next approximation that we are considering. So the main idea in this approximation is you will assume density to be constant everywhere. So you will have the same continuity equation, but then we'll have an extra term that is coming here. This is basically the source term that you will be getting here. This is basically your buoyancy force system. So again, I have already taken all the approximations for boundary layers, so you do not have the pressure terms. Because we have a flat plate, the pressure term is also gone here. Otherwise, you would have to take into account those terms as well. Because viscous heating is neglected, the other term is removed here. Similarly, along the y direction, we have removed those terms because we have assumed it to be fully developed. Now, next comes the scaling analysis, where you have to decide what are the relative scales for each of these variables we have considered. For x, the scale is, if you see, for x direction, the scale will be delta. For y direction, you can take the scale to be the length of the plate. Similarly, for u is along the horizontal direction, that is where the boundary level, the horizontal velocity will be, that is alpha by delta t, and v will be alpha h by delta t square. How do you obtain these two? You can choose one of them and substitute in the continuity equation, then you will get the other term. So for example, if you choose u to be alpha by delta t, then if you substitute back in this equation, so this will be alpha by delta t and this is delta t square. So y will be in terms of h. So v should be alpha h by delta t square. So that is the term that you will be getting here. I hope you have already gone through the lecture video, so I'm going a little fast in this. Similarly, you'll get order of each of the terms in the momentum equation and the energy equation. And now the most important part here is understanding which of these terms can actually be neglected and which should not be neglected. Okay, there is a y missing here. Okay, I'll just correct that once I upload it. So this is the inertial terms. The order of inertial terms is following this particular expression. Then comes the viscosity terms, and then comes the buoyancy terms. So depending on where you are, depending on what the Prandtl number is, there will be a balance between two of these forces. So we have different scenarios. The first scenario is when the Prandtl number is very high. So if Prandtl number is very high, this particular quantity will be very less. So the balance will be happening between these two forces. So it is a viscous force versus the buoyancy force. So they should be of a similar order of magnitude. So from that analysis, we'll obtain the scaling for delta t as RAH to the power minus 1 by 4. This is again valid only for laminar, as we started out with, is for laminar case. So if delta t goes as per this particular scaling, then we can arrive at a relation for Nusselt number as RAH to the power 1 by 4. We do not know what the actual constant is, which we will solve in some time. But we'll have a rough estimate of what this actually goes out with. So if you know the Rayleigh number at one point and Nusselt number at one point, you can just use nu1 by nu2 equal to RAH1 by RAH2 whole to the power 1 by 4. And then comes the next scenario where Prandtl number is very much less than 1, say for liquid metals or something of that sort. Then this particular value will be very high. So what we have is the balance between the inertial forces and the buoyancy forces. So this term should be of the order of 1. Why we are considering this to be order of 1 is because that is the driving force. So all of this are under the case of natural convection. So this should be at max equal to this. If it is higher than that, then that is of no point. Like buoyancy force won't be the driving force in that particular case. So with this, we'll have delta H going as whatever we have previously, but just that we have Prandtl number account to be Prandtl number has also be should also be accounted for. So similar way, we can obtain the scaling for Nusselt number here, which will scale as RAH to the power 1 by 4 times Prandtl to the power 1 by 4. We introduce a new number here, but this should be fairly straightforward. But the other case is here we are saying the balance is between the inertial forces and the buoyancy forces, but so which means the effect of viscosity is nowhere to be seen. So what happens in such cases is when Prandtl number is very much less than 1, you have two different regions. So one region is where you have the balance between inertia and buoyancy forces, and then the other region which is close to the wall where you have the balance between friction and buoyancy forces. So close to the wall, U and V will be close to 0. So the effect of inertial forces will be negligible in this particular portion, in this small region. So what is the scale of this extent of this particular region is denoted by delta nu, and the scale for that would be obtained if you just balance the terms on the viscosity and the buoyancy terms. So from that you can obtain the scaling for delta nu as Grashof number to the power minus 1 by 4, where Grashof number GRH is basically the Grashof number as Rayleigh by Prandtl number. The next step is you non-dimensionalize your governing equations by again choosing whatever we have. So while non-dimensionalizing, we are not using delta here, which we will do in a little time later. But if you non-dimensionalize with H, this is just to understand how many parameters you have to will actually define the problem completely. So we have two equations, basically three equations: continuity equation, y momentum equation, and energy equation. And I have so many things that are in my like for example, if you see the problem as such, we need to know the velocities u, v, x, y. Beta is the thermal expansion coefficient of that particular gas. Nu, G, T infinity, and TW, the wall temperature, is the boundary condition. So we have a lot of parameters here. So we are trying to reduce this number of parameters by using non-dimensionalization. So the whole idea of non-dimensionalization is to reduce your number of parameters. So once you non-dimensionalize with these particular values, so these are the final equations you are coming up with, which has only two numbers. One is the Grashof number, and the other one will be the Prandtl number. here we have this equation we have written in terms of REH and GRH, and we define a new number called Richardson number. Now, depending on what the value of this Richardson number is, you will decide which type of what kind of convection it is. So if that particular value is very much greater than 1, then you can consider it to be natural convection. If it is less than 1, then you can assume it to be forced, and if it is equal to 1, then it is mixed or combined. And we are choosing REH to be square root of Grashof number, so that it's for RAH equal to 1. These are different scalings that you would obtain for different values of velocities, and this is a thermal boundary layer thickness, and then you have the wall to velocity peak, which is basically the delta nu that I have been discussing little time before. Velocity is the V magnitude and Nusselt number correlation, and the scaling relays, but we still do not know what the actual constant values are. So that's where the next thing comes. So in order to obtain these values accurately, we need to be able to solve the non-dimensional equations, but then you have a lot of unknowns. So either you have to go to some CFD or something, but alternatively, you can use similarity equations. So the idea in these similarity equations is when you see the velocity profile or say the temperature profile, whatever it is, we are seeing that if you have a point y1 here and another point y2 here, so the velocity at this particular point and this particular point are similar to each other in a way that if you have some reference velocity such that u by u, the velocity here by velocity here is proportional to this the locations in some particular power law, which we do not know as of now, which is something that we'll be identifying a little later. What that assumption translates to is you are saying that the entire equations will be governed by a parameter called eta, which is called the similarity variable, which is defined by x by delta t, where delta t itself is a function of y. So instead of saying we have two unknown variables x and y, we are converting them into one unknown variable. So that will kind of simplify the equations. And once you substitute this and identify the appropriate scaling for, now if I have written like this, then I need to know what delta t is as a function of y. So from the scaling, we know that delta t will scale as RA to the power minus 1 by 4. So we use that particular relation here. We do not know the constant. We'll start with assuming it to be 1. And once you solve the equations, you will obtain what this actual constant value is. And we also non-dimensionalize the temperature here with respect to this T minus T infinity by with respect to the wall temperature. And this V is the vertical velocity that we are aiming to find, which we already know before as it will scale as RA to the power half. You can obtain this also from the streamline function. So you can take the streamline function as this and then do V equal to del C by minus del C by del X and U equal to del C del Y, whichever way you are coming up with. Once you obtain these values, you substitute them back into the governing equations to obtain this equation with appropriate boundary conditions. So the boundary conditions are basically at wall, you have the velocities to be 0 and you have temperature to be equal to TW. At far enough from the wall, you have temperature to be T infinity and velocity should be 0. When we were solving forced convection problem, we have a constant velocity even outside, but here it is not the case. So before going on to the correlations, so how do we, are you familiar with how to solve this kind of equations? Okay, I guess maybe some of you are familiar and some are not. Maybe whoever is watching. So let's say if I have equations of this kind. Since this is not discussed in the lecture video in detail, I'm just taking a little more time here. So this is the governing. These are two equations that we have, and we are trying to solve for f and theta, provided the boundary conditions. So this is a third order differential equation. So f should have 3 boundary conditions, and theta is a second order differential equation. So it should have 2 boundary conditions. So in total, we'll have the conditions as f of 0 is 0, 0 is 0. F prime is something that is proportional to v, and f is something that will give us the value of the stream function. So this is a reference point that we have taken. F prime of 0 is 0, which essentially translates to saying that the velocity, the vertical velocity at the wall is 0. And similarly, the vertical velocity, if you go far infinite, like far away from the wall, should also be 0. Similarly, for theta is my non-dimensional temperature. Theta is defined as, so you have at the wall, you have this equal to be 1, and very far from the wall, you have this equal to 0. So how do we solve such kind of equations? So if you have a simple equation, so just to give a brief intro of what you do. So let's say you have an equation, simple equation of sort dx dt equal to f of x. And then you have some initial condition, x of 0 equal to x naught. So this kind of problems are called initial value problems. So you'll be given an initial condition and you'll know how the dynamics go with respect to time. So all you have to do is if you use a very simple method, like say Euler method or something, you just take the finite, like do it in a finite difference kind of thing. So you just say x of t plus 1 minus x of t plus delta t minus x of t by delta t equal to f of x of t, and then you obtain x of t plus 1 t plus delta t. All you have to do is this, but this is a very simple case, like this is called Euler method, where you do the forward case, not the backward one. So forward in the sense that you are taking the derivative in the forward direction and you are using the value of x at the previous time step. So and then you keep doing this. So you'll start with delta t equal to 1, delta t equal to 2, and so on. Eventually you'll be getting x1, x2, and so on. So if you make a plot of it, you will get the value of x, how the value of x will change as a function of time. This is a simple case. Now imagine if you, instead of having x as a scalar, if you have a vector, you do the same thing, but instead of one value, this will be a vector, f of x will be a vector, delta t will be, so this will be like addition of two vectors. So that's the only thing. So all we have to do is first convert this problem into something of this sort. So we'll define new variables. So let's say if I call f0 as f, because there are no derivatives, f1 I will call as f prime, f double prime, and similarly let's say I'll call theta 0 as theta and theta 1 as theta prime. So my equations will be, the first equation is let's say f prime is f1, which is equal to f0 prime, or let me write in the same thing. So f0 prime is basically f1, f1 prime is f2, f2 prime is f3, f3 is basically f triple prime. So I can substitute this equation in terms of f triple prime. So that would give me theta minus 1 by Prandtl number times f prime is f1 square by 2 . So now I have f0, f1 prime, f2 prime. Similarly, I can write for the other two also. So theta 0 prime will be theta 1. Theta 1 prime is basically theta double prime. So theta double prime can be written as 3 by 4 times f0 times theta prime is theta 1. So if you consider x as basically this vector, then all we are saying, this is the derivative of x with respect to eta. So dx d eta is some function, let's say some capital function, capital H of x, where h of x is this function. Like if I put all of this in some matrix, some vector kind of way, so that each one of them are each components, then this is basically the equation I will be solving. But then this is how the equation is there. The next step is to get the boundary initial conditions. So x of 0 equal to x naught. So what are the x of 0? If I want to write x of 0, I know f0 of 0. f0 of 0 is f of 0. f1 of 0 is f prime of 0. f2 of 0 is something that I do not have. Theta 0 of 0 is theta of 0. which is 1, and theta 1 of 0 is theta prime at 0, which is basically the at the wall the derivative of non-dimensional temperature. This is something that is important because that will give us the Nusselt number, which is also something that we do not know. So what is usually done, like if you know these values, then we'll be able to solve this problem. But since we do not know these values, the technique that we use is we'll assume these values, let's say some a and b. You'll assume the value. You will integrate this equation, obtain the value of x in terms of eta, and then compute these values. So once you get these equations, then you know this is f0, f1, and this is f1 prime. So this is my f, this is my f prime, this is my f double prime, this is theta, and this is my theta prime. So once you solve this equation at eta tends to infinite, so you'll take some large number of eta, some value. So beyond some particular value, you will see the value of f prime. This is something very similar to what we have seen in the forced convection boundary layer as well. And that f prime should be equal to 0. So if that is not equal to 0, you will change the value of a and b. Similarly, you will take for theta value, and this theta value as eta tends to infinity should be equal to 0, which if it is not matching, again you will change the values of a and b. So you will keep iterating till you find the correct values of a and b such that f prime at eta tends to infinity is 0 and theta at eta tends to infinity is 0. Is that clear? How do you update these values of a and b? Again, there are several techniques for that. For people who are interested, you can say some techniques like say Newton-Raphson is one technique that you might already be familiar with. So this is basically a set of nonlinear equations. All you have to do is use a technique like Newton-Raphson or any other technique that you know, any root finding algorithm you can use and find this thing. Estimate the values of a and b, like find the values of a and b such that these conditions are satisfied. Once you solve that, you will obtain the expressions for Nusselt number and the heat transfer coefficient and Nusselt number, etc. So these are the limiting values given to you. The correlations are given to you directly from there. In today's session, maybe I'll show you some way to do this, how to calculate these values using say Mathematica is one tool to do that. If you're familiar with say MATLAB or any other tool where you don't have to manually do this entire stuff. So all these things can actually be automated, can be like there are already algorithms, people have already done them. All you have to do is just use the correct solver, which will give you the direct values of this. Only these initial guesses need to be provided sometimes. Sometimes you don't even have to provide them. So I'll show you today in Mathematica how to solve it. You can explore other tools also. Once you know the methodology, it should be straightforward. Okay, are there any questions? The heat flux case is also very similar. The major difference between these two that you would see is when you have a uniform wall temperature, T is constant, but then your heat flux will actually vary like this. Very close to the leading edge, you'll have high heat flux because that is where the temperature difference will be higher. But as you go higher and higher, temperature will keep increasing and eventually it will reach a constant value. The same applies for the uniform wall heat flux where you have the Q to be uniform, but then the temperature will actually keep on increasing as you go along the length of the wall. But if you imagine this, like eventually what would happen is if this is infinitely long and both of these are infinitely long, eventually this would also become straight line and this would also become straight line. So you wouldn't be able to differentiate between these two. And that happens once you have turbulence set into picture where both the uniform wall heat flux or uniform wall temperature will actually give you the same values of heat transfer coefficients, which we will see sometime after some weeks once turbulence actually comes. Then you can realize that. But for now, in the laminar exam, these are the profiles that you will be seeing. Another important thing is the Rayleigh number that we have defined previously uses the concept of temperature difference delta T, which is given by TW minus T infinity. But once you have a uniform heat flux condition, we do not have any reference wall temperature. So the Rayleigh number has to be changed accordingly. And the changed Rayleigh number is given by this expression where delta T is replaced by QW prime Y by the thermal conductivity. So that instead of delta T, we are writing it in this particular form. They are kind of saying so basically we are writing QW prime as, I wouldn't say equal to, so this is basically we are scaling this as K times delta T by Y, so that delta T would scale as If you were to write it more accurately, then it should be something like by delta, but instead of delta, we are writing it this way. So this would scale in this particular way. This is just to define the Rayleigh number, but what would happen eventually is whether it is just like I said now, whether it is uniform wall temperature or uniform wall heat flux, the correlations that you're going to get will eventually be the same. Just that you have to adjust for the corresponding factor inside your Rayleigh number. Are there any questions up until here? Yeah, this is just a brief recap, so I don't think there would be any much questions if you've already gone through the lecture videos. So we'll solve some problems. These are straightforward problems, but I just want you to demonstrate some tools so that you don't have to manually do all of this again and again. So let's say you have a vertical wall of an oven which is 60 centimeter long and is covered with a metal sheet maintained at 170 degrees Celsius. Air temperature inside the oven is 90 Celsius and pressure is atmospheric. Calculate the local heat transfer coefficient at the end of the wall and the average heat transfer coefficient over the total the entire surface of the wall. Here there are two things. It is not directly mentioned here in the problem that you have to use constant wall temperature or constant heat flux. Nothing is mentioned in the problem. So it's like you have a oven wall and then you know that there is some metal sheet and then you have measured temperature at some particular point and this is a value that is being reported to you. So how do you know which assumption to use? Constant wall or uniform heat flux, or how should I go about solving this? Like I have given the heading here, but other than that, so how would you go about it if you were to solve a problem? You don't know, you know that there is a metal sheet and then there is a wall and you have to decide whether you should go with constant wall or uniform heat flux, or maybe there is non-uniform wall temperature, there is non-uniform heat flux, maybe some other complex model is required. So before doing that, how would you go about it? Any guesses? Is the question clear? Okay, the major point in the problem is that we are saying that it is to be a metal sheet because metals have high thermal conductivity. So what you can assume is the conduction inside the metal is actually happening way faster than however the flow is changing outside the metal. So what that means is saying that even if, for example, if suppose there is a temperature gradient in the metal for some reason, let's say the airflow outside is different or something happened and some local cooling or local heating happened and temperature distribution changed inside the metal. What would happen is because it has very high thermal conductivity, heat would flow eventually and make the temperature uniform throughout. So first thing is we can, whenever you see a very high metal or any metal sheet or something, you can assume it has a high thermal conductivity, which will give us a uniform distribution. We do not know whether it is constant or not, but we can assume that to be uniform. Because in the problem, it is said that it is maintained at 170 degrees Celsius. So if at least one point is maintained at 170 degrees Celsius, because it is assumed to be uniform, you can come to the conclusion that it is a constant wall temperature scenario. Is that clear? So all we are asked to find is the value of H. So in order to do that, first we need to know the Nusselt number. Like once you know the Nusselt number, that would be straightforward. So you have Nusselt number given by Hy by K, and from this you can calculate the local heat transfer coefficient. And in order to calculate Nusselt number, you need to know Rayleigh number, for which you need to know all the properties, alpha, nu, and beta. All these values should be known, but all these property values will change with temperature because we are considering air here. All of them will actually vary with temperature. So even just like before, when we were discussing duct flow, here we define something called film temperature, which is the mean temperature of the wall and the fluid. So we have to consider the film temperature and evaluate all these properties at the film temperature and use that to determine the value of the heat transfer coefficient. And the property values will usually be given to you in something of this sort. So there will be some certain temperatures where all these properties would actually be measured, and the temperature that you get would actually be falling somewhere in this, and then you can use a linear interpolation between those two. For example, if in this particular problem, the mean temperature is 170 plus 90 by 2, so that would be around 130 Celsius. So for 130 Celsius, you can take the average value of between 120 and 140 and get all the property values. So that would be the first step. Once you get the property values, and you have to solve for this equation, for which I'm going to use something called Mathematica. How many of you are already familiar with this tool? Okay, there are a couple of students. So have you used this before? Okay, I guess, should I consider it as yes or no? Okay, maybe there will be someone who haven't used it. So this is basically a symbolic tool, where symbolic is essentially like, say, if you're familiar with any programming language, we usually deal with numbers. But here it deals each of these values as separate objects, and then it will treat them as just as we would do while you are doing hand calculation. So it would treat G as G, beta as beta, instead of directly substituting the values. It will compute these values, insert them into different equations that you have, and then it will actually solve it just as you would solve analytically on pen and paper. But it has its own function, so you have to just since it is a programming language, you have certain rules that you have to follow in the way you write the equations. So the first problem, it is a constant wall temperature problem. So all we have to do is get our governing equation first. The governing equation, in the sense uh, the ones that I have shown before, that f triple prime, the equation in terms of f and theta, and then solve those equations and get the value of theta prime at the wall, which will give me Nusselt number, from which I'll calculate the heat transfer coefficient. So what we do here is the way to define the terms is something like this. So you just write the symbol name, whatever you have, equals to, followed by whatever. You don't have to declare any of these variables in this particular tool. All you have to do is just write the equation as is. What it will take is, if you leave space between these two variables, and it will treat that there is a product between those two variables. So parenthesis is like grouping, like that's how you would write normally on pen and paper. This is for the power and nu and alpha. So I've defined the Rayleigh number first, followed by eta. Eta is basically our similarity variable, which is x by delta. Eta is basically x by delta, and we have delta scaling as Ra to the power minus 1 by 4. So if I substitute that back, eta would scale as x into Ray to the power 1 by 4 by y. So if you just substitute that back here, and then I define psi is my stream function, which is alpha times Ra to the power 1 by 4 times f of theta. So the way here is the square brackets. Whenever you have square brackets, that essentially denotes that is a function. So when I write f square brackets eta, it means f is a function of eta. Next, we have to find u and v. U is basically del psi by del y. So d within square brackets is d is basically the differentiation operator. So derivative of psi I'm doing derivative with respect to y. So this will calculate u. Similarly, V is basically minus del psi del x. So this term is basically minus take derivative of psi with respect to x. And I'm defining the temperature as T naught plus TW minus T naught times theta. Again, theta is a function of eta, so I have to write in this particular way. Then we have to write our momentum equation. Momentum equation is U del V del x plus V del V del y equal to nu times del V del x2. So what this term basically means is take the derivative of V with respect to x twice plus g beta t minus t naught followed by these operators. What I'm writing here is just writing it a set of instructions to how to simplify this particular equation. So what it does after that is, let me show you the final. It will take in the equation, it will write them together, and this is the final equation that I'm getting. So if I just simplify them a little more, the similar way I will write my energy equation, which is U times del T del x plus V times del T del y equal to alpha times del square T del x square. And then you just simplify that equation. These are all default functions available in this tool. That's so that this will simplify a lot of your hand calculations. So this will be the equation I'm getting. So this term in the bracket is basically my eta. If you recognize this particular term, this is basically by eta. So this entire thing is my Rayleigh number, and this is x times Ra to the power 1 by 4 by y. So this entire term is basically by eta. So what I'm doing in next step is substituting eta in place of this entire big term over here. So which once I have done, so my equation becomes something that you have seen a little time before in the slides. So this is my equation. So 4 times Prandtl number theta as a function of eta minus 2f prime eta square, 2f prime square plus 3f f double prime minus 4 Prandtl number times f triple prime. This should be equal to 0. And similarly, the energy equation. The energy equation is 3f theta minus 4 times theta double prime equal to 0. So the next step is to solve this particular set of equations, which is performed by again a default function. So in order to solve the equation, all you have to do is write this function ndsolve, which is basically numerically solve the differential equation given by momentum equation equal to 0, which is basically this equation, followed by energy equation and the boundary conditions. So the boundary conditions I have given are at f of 0 equal to 0, f prime of 0 equals to 0, theta of 0 is basically at wall, it should be equal to 1. And the other condition we have is when you are writing it mathematically, like on pen and paper, we say that eta tends to infinity, but we don't have to actually solve till eta equals to infinity. We have to give some big number. So when we were solving the forced convection boundary layer, you remember, if you recollect, the eta value was around say 5.6 or something. After that particular value, f prime was not changing, like it will be close to 0. So in a similar way for this problem, after a bit of trial and error, you will find that when it is close to 10, the value is actually going to 0. So I've taken that the boundary condition, like the eta value to be 10 here. Similarly for the other theta also, at value of eta, instead of saying eta equals to infinity, I'm keeping eta equals to 10 because we need a finite number so that you can numerically solve these equations. And what this operator tells me is substitute PRT in place of PR in all these equations. So because if you see the governing equation has two variables, f prime theta prime, and then we have one more additional variable called the Prandtl number. So unless we specify the Prandtl number, we will not be able to solve this equation. So what this line tells it is, okay, substitute PRT, which is given by the user. Take the PRT given by the user, say 0.7, 0.1, 1000, whatever number you give, take that value as an argument inside the function, substitute that into the Prandtl number given in these equations. It will do the substitution, solve for f and theta in the range eta from 0 to 10. Once it solves the equation, the solution will be stored in the f1. So with this till here, I've just kind of translated what I have written here. The most important thing is getting the solution. So for which you have to take in the air properties, which are I have taken from the CSV file in my. I've downloaded the air properties and saved in a CSV file, which I have loaded it here. Then these are some there just to kind of make sure the units are consistent. And finally, as I said before, the temperature that you might be getting as a film temperature would be different from the actual temperatures. You have to use some kind of interpolation. So what this interpolation does is it takes the values. You will specify film temperature, it will interpolate at that particular temperature and give you the property value. So all you have to think of these lines is basically is you tell a temperature, it will give you that particular property. If you use nu I, it will give you the value of mu at that particular temperature. If you give beta I, it will give you the value of beta at that particular temperature. All you have to do is call this function beta I given that film temperature. So we'll take the problem parameters. The film temperature is half of 170 plus 90 and give all other values. G is 9.81, beta is the beta I, TW is 170, etc. Whatever values are given in the problem you will take. And the most important thing that we need is the theta, the heat transfer coefficient. The way we define heat transfer coefficient is minus K del T del X divided by TW minus T naught. That's how we have defined the heat. So if you recollect, so QW prime is H times TW minus T infinite, which is minus K del T del X. Once you substitute X equal to 0, from this you can get H. This is exactly what I have written there. So once you substitute all these values, so H is given as a function of Y. Once I have H as a function of Y, all we have to do is, again, as I said, to substitute, you have to write this particular operator. So in the expression of Hy, put Y equal to 0.6 because the length is 60 centimeters. You convert it into meters. So that is giving me around 3.08. And the next thing is determine the mean heat transfer coefficient, which is how do you obtain mean heat transfer coefficient? H bar is 1 by L integral 0 to L H of Y dy, which is again a simple line in this particular tool. So all you have to do is write integrate Hy with respect to Y from 0 to 0.6 and then divide that with Y. In this entire expression, the value of L is basically Y. I have denoted Y with L. So Y you have to substitute 0.6. Then you will get the mean heat transfer coefficient. Since this is kind of a lot of things have actually been simplified because this is a very high level language. Yes, so you don't have to worry about how to actually solve the differential equation. It is directly provided here. So the important thing that we can get out of this, like once you do things like this, is say for example, if I ask you to find the velocity components or some, because Nusselt number is one way to do it, but then if someone asks you to find velocity, so how would you go about solving for velocity? Say if I want to plot velocity, so this is one solution where I have actually plotted the velocity as a function of x. So beyond x equal to 0.04, like I can say, for example, if someone asks you to calculate delta, how do you calculate delta? Those are other questions that you might, in order to answer such questions, you need to know what the actual solution is. So you need to know what is f of theta, what is theta of theta. Without knowing them, you cannot solve this problem. So what this particular function does is it will solve that equation and then give you some functions. So those functions are basically like, you can think of them as some table of values. So eta will be given, f will be given, theta will be given. So it will be like at every eta it will be given. So if you ask the value of function at a different point, it will take a linear interpolation between these two values and give you the value of f and theta at that particular value of eta. So let me ask a question before showing you the answer. So let's say if I ask you to find the value of delta here, how would you do it? Like I don't want expect you to write the equation or code or anything, but just the approach. How do you go about finding eta? Sorry, delta, the boundary layer thickness. Maybe I should show you these equations. Calculating heat transfer coefficient is clear, right? Are there any questions? Yeah, you can always take the correlations that are already there in the literature instead of actually solving the differential equation. You can take the correlation for that given in terms of Rayleigh number or Prandtl number, compute the Rayleigh number, and use the Nusselt number. From there, calculate Hy and H mean. That is also there, but I just want to show another way as well, because since we are now we have tools that actually solve the differential equation. It should be straightforward. So let's say now if you are asked to find delta, how do you go about it? I know f of eta. So basically I have eta, f and theta, And let's say since I have f and theta, I can also calculate f prime, f double prime, and theta prime. I have all these values from eta equal to 0 to whatever value I want. I can compute all these values. I can use that function and solve for this equation. I'll get all these values. The question is now I need to find what is delta. Delta as a y function of y, or let's say, just put it simple, let's say delta L, for which is basically delta at y equal to 0.6. How do I compute this? With this known, all these values are known. Is the question clear? Why do you think we will actually need the value of delta? If you recollect, when we were actually in last week lectures, when we were having kind of a pipe flow, we have two different regions there. So you have something called an entry region, entrance region, or entry length, and then you have the fully developed one. Even there, we need to know an estimate of delta, because we say that if this particular whatever diameter d is way higher than the boundary layer thickness at that particular length, then you can safely assume that you are in the entrance length region, right? The similar way, if you have what happens is you do not have just one vertical surface. In reality, what you see is, say for example, if you are sitting in a room and say, okay, this is, say you're in a place where you do not have fan or air conditioning or anything, and you are in some large room. So you are in some big room. So you have several different walls in different locations. So in absence of fan and all these cases, so we always have natural convection across these walls. And because this for now we'll assume that you can still assume 2D, laminar, and all those assumptions are valid. In under those scenarios, the question is, can we assume that this to be a flat plate? Because there are other walls also nearby. So would they influence this particular the natural convection happening near this wall or not? That is where you need to have an estimate of these delta values. So if the delta, if the walls are say very close to each other, such that the delta is actually is of the same order of magnitude as the separation between the walls, then what would happen is both the boundary layers will actually interact with each other. Then some new flow physics would actually be developing there. But if these are sufficiently far apart, such that the distance between these two is way higher than the boundary layer thickness, then you can safely assume that both of them as two separate uh, flat plates, and you can use whatever correlations that we are developing here. So in order to make such kind of reasonable assumptions, you need to have an estimate of what delta value actually is, instead of knowing that delta will be order of so and so. So for that, how do you estimate delta if I have these values? So you go back to the definition of how we defined it. So we have defined eta to be, and now I know all the property values because I know the film temperature and I can compute all the property values. So I know what the Rayleigh number is. I know what the y is because I have specified y to be 0.6. So Rayleigh number is basically, so with this Rayleigh number, and I can substitute y and get the Rayleigh number. So these terms will be known to me. And the way we define delta is basically beyond that particular delta, the velocity or the temperature. If it is delta T, the temperature. If it is velocity, it is the hydrodynamic. So that should be equal to 0. That is how we have defined it. So from what we have, when we are doing the simulation, we found out that the velocity profile that I have shown you just now is something of this sort. So beyond a particular point, the velocity will actually go to 0. And the corresponding eta value when you observe these values, f prime will correspond to the v, like f prime will be proportional to v. So f v is minus alpha times ra to the power half times f prime. It goes something like this. So what we are trying to do is find that particular value of eta where this will be close to 0. So when I've done it, this is close to around say 10 or something. It's like a little less than 10, but if you take it to be 10, so all you know is this eta will be 10, and the value of x at that particular eta is my boundary layer thickness. Delta times this entire quantity, whatever you have calculated now. So this will give you an estimate of what the value of delta can be. So with the values of eta that I know and the function that I have got from the solution by solving the solution that I have before, I got the value of delta to be around 4 centimeters. So when I have a plate of, 4 millimeters. So when the plate length is around 20 centimeter and the temperature difference is around 80 Celsius, the boundary layer thickness is around only millimeters. It's around close to 4 millimeters. And this is the plot of the velocity profile, and the maximum velocity is around 0.6 meter per second. There can be different other questions you can ask from this. Say, for example, you can ask what is a shear stress acting on the wall. How would you go about calculating that? Is again straightforward. All you have to do is calculate del v del x at x equal to 0, and that should give you the all shear stress. Any other questions that you have, you will be able to solve it once you know these values. We should be able to back calculate from them. Are there any questions? Okay, there are no questions. Then we'll move on to the next problem. So the difference between that and this here is also a metal plate, but then the only difference is we are saying that it is heated electrically, and the wall heat flux is specified as 15 watt per square meters. So the main difference is the previous one and this one, still the metal plate, so the temperature will be more or less uniform. But then the question is, because we are heating it electrically, we are specifying what the heat flux is at each and every point on the surface of the plate. In the previous case, it was not specifically mentioned like that. So again, you are asked to find the local heat transfer coefficient and the average heat transfer coefficient. So how would you go about? Maybe I'll wait for a couple of minutes. So the procedure would be same. I don't expect you to solve the governing or the differential equation, but you can just write down the steps that you would be doing, that you would actually do to solve this. Because in order to solve this, you anyway have to solve it numerically, which is not there in the scope of this particular course. So the numerical part I will leave aside, but the steps should be clear, right? So you can just highlight, outline what are the steps that you'll be following to solve this one. Do you find any difference between this problem and the previous one, like other than the boundary condition? So the main challenge between the previous one and this one is if you try to calculate it, you can always get Nusselt number. But this Nusselt number will be some function of Rayleigh number and Prandtl number. And how do you obtain these numbers? In order to get these numbers, you need to know the property values. And all these properties values should be evaluated at the film temperature, which is because it is a constant heat flux, your temperature will not be constant throughout the wall. So what would happen is you'll have a temperature that will be varying as we have discussed before. So it will be as something like this. So the delta T will be proportional to y to the power 1 by 5 under the laminar cases. So what will happen then is your temperature will be continuously varying. So you'll have to come up with some kind of a mean temperature. And at the mean temperature is what you will take the film temperature, like the TW mean plus T infinite by 2. Maybe I will just put here to avoid confusion. That should give you the film temperature, and that film temperature you should use to calculate these property values. But the question is, I do not know the value of this. How do I find the value of TW1, like the mean wall temperature? If I know this, then it is straightforward. You calculate film temperature, calculate the properties, substitute into your correlation, whatever correlation you have that you will find, or you solve the similarity equations and then get the value. Whatever it is, you can do. But in order to do any of that, you still need these values. This is an unknown, and this itself will actually depend on the solution that you are going to use. So how do you formulate this? Like how do you solve these cases? Is the question clear? Maybe you need some time to think. So I don't want you to solve the problem. Just tell me the approach that you will be following to solve this particular problem. Like you do not know the mean wall temperature. So unless you know that, you will not be able to find the film temperature and evaluate the correct properties. You know the correlation. Let's say the correlation is given to you somehow. Like you know if this is the Rayleigh and Prandtl number, you will know the Nusselt number from which you can calculate heat transfer coefficient. Like once you know Nusselt number, calculating heat transfer coefficient is straightforward. If it is local, then you just calculate with respect to y. If it is the average one, then you can just integrate that over whatever length you have. These two are straightforward once you know the property values, which themselves are dependent on TW, the mean wall temperature. That is a problem. So maybe I'll wait for a couple of minutes. So if you have any suggestion. So let's say this is something very similar to what we have discussed little time back, where I was saying the problem of the initial value problem, where if I would have known the initial condition, I would have solved it straightforward. But the problem is I do not know the initial condition. So I have to assume some values and then do something. So we can use a similar strategy here also. What we have to do is we have to assume a mean temperature and then compute all these values, say nu, alpha, thermal conductivity, whatever properties you have, you compute like from the assumed value of TW bar, and then compute the Rayleigh and Prandtl numbers from those. Again, I'll just put them here. I'll just write directly. Assume a value of TW bar and then the mean wall temperature and compute Rayleigh and Prandtl number from there, from which you can estimate Nusselt number. Till here it should be straightforward, but what should I do after this? How do I know whether whatever I've assumed is correct or not? Like I need some feedback so that I will know whether I am good or bad, whether my estimate is good or bad, and then update it accordingly. That's how all these iteration strategies work out, right? Say Newton-Raphson or any of that, you start with an initial guess and see whether you are close to your final route in some way. So you'll either calculate the gradient or something and say that whether that particular value is approaching zero or not. And depending on how close it is to zero, you'll decide whether to stop iterating further or not. So the basic strategy is the same. So we need to come up with some criteria that will tell me whether my choice is good or bad. And then depending on how good or bad, I will decide what my next choice is. So what would that be here? If something is not clear, let me know. So I need somehow an estimate of what this TW can be in some another way. So I should be able to calculate TW in some other way and compare with whatever values I have obtained here and see how consistent these two values are. So what would be the other way to compute TW? So let's say I know the Nusselt number. I can compute my H. From this I can compute with whatever properties I have calculated before. I can compute the value of H. And once I have H, I know that QW is H times TW minus teens, right? So from this I'll get an, here I'll have, let's say Ty, and once I have Hy, I'll get TW of Y. And once I have TW of Y, I can always compute TW bar. Like all I have to do is integral. That should give me TW bar. And what happens is, what if your initial guess is bad enough, after doing all of these steps, whatever value of TW you are getting here, let's say you started out with the temperatures are, say 90 Celsius is given here. Let's say you started out with 90 Celsius initially. After doing all of these steps, at the end, whatever TW you'll be getting, like from this, let's say you'll get another, maybe I'll just split this into two more steps. Let's call this TW bar prime. This TW bar prime, you might end up with say 94 or something. So this 94 and 90 are different from each other. So what you would do next is you will take this assumed value, substitute that back here, and again propagate it through like this. So then what would happen is you will take 94 and then do, let's say you'll end up with say 96 or something. And then when you substitute 96 back, you'll get say 96.1 or something. Then like if you keep doing, then eventually you will reach a point where these values, the difference between this value and this value will not be changing so much. So depending on what level of accuracy, if you require 1 decimal place accuracy, you might have to do say 2 to 3 iterations. So if you require to say 2 to 3 decimal places, then you might have to do more iterations. But the idea is this. Is the approach clear? This particular method is called successive substitution. This is the this particular technique has been used in several of the solvers that are already there. but then this particular technique won't work for all the cases. So there, your problem needs to have a certain structure for this particular technique to work. So the values that you're going to predict, the changes across iteration to iteration, we are assuming that it will actually reduce and eventually it will converge. But if the problem has some more nonlinearities, or if it has some exponential terms inside, some power terms inside, which will increase the errors as it propagates, and what would happen is the difference between these two values will actually increase, and then eventually it will diverge also. So you have to give appropriate initial guess, so that when you are close to the solution, then it will actually converge. For this particular problem, it actually converges with this particular technique. If not this particular technique, then you might have to use some other technique also. That is up to you. But is the approach clear? The idea goes the same. The way we are updating here is what matters. So after in successor substitution, what we are doing is take the value of TW prime and make that as the next value of TW. That is the approach. But then there are other techniques depending on, you take the difference between these two values and decide if it is higher, you do something, if it is lower, do something else. Then you can also come up with other strategies, wherein you take a certain percentage of this value and certain percentage of this values and decide that to be the new value. So something like, say, alpha times TW prime plus 1 minus alpha times, okay, maybe I should use a different symbol because alpha is already used. Let's say r times this and 1 minus r times this. But different strategies are there to actually make this converge. We'll not go into that, but the basic idea is this. So the same tool I have taken, but there are some key differences in the way you solve this particular problem. So the Rayleigh number is defined in a different way, where you have g beta instead of delta t, we are writing as qw y by kappa. Kappa is your thermal conductivity, and then y cube by alpha. So eventually you'll get this term. Delta is again defined in the same way, but then the key difference here is previously we were having minus 1 by 4, now we'll be having 1 by 5. So if you would keep 1 by 4 here, what would happen is you would not get in the similarity form. So the assumption that we are considering here is the self-similar assumption, that the velocity or whatever that we are having here is something called self-similar. So you have the same profile, like kind of a similar profile that is keeps going on as you increase the y. That is the basic assumption on which the entire derivation is made. So if you have chosen wrong scaling, what would happen is if this self-similar behavior is existing, then we would actually not require two variables. Knowing one variable is sufficient. So if this exists, then I don't need x and y. Knowing eta alone is sufficient to solve the entire problem. I don't have to know what the exact values of x and y are. That's the main simplification that we are getting by this assumption. And physically, what this assumption means is, if I know the velocity at y1 and I know what y2 is, I can compute the entire velocity profile at y2 just by knowing this, what is y1, what is y2, and this velocity profile. I will be able to compute this. So what that also means is the flow has reached a point where it doesn't depend on how it started out with. We do not care what happens here. It doesn't matter to me what happens here. If I know velocity here, I can compute here. Similarly, if I want to calculate at a different point, I don't care what happens here. If I know this one, then I'll be able to do this. So this is something called memorylessness, where the flow actually forgets how it started, but eventually gets into this particular stage. This is kind of an assumption where you do not have any obstructions. Let's say if I have an obstruction like this, then what happens is near the obstruction, the flow will actually depend on, like the flow will eventually go here and say divert like this. So if I have something like this, then I'll have something like this. So the self-similar assumption may not be valid in several regions like this. Say some corners or something, it might not be valid, but in the rest of the regions, it might be still valid. So whenever you're using these correlations, you have to be careful, as in not applying in them scenarios where they are not applicable. The major hypothesis here is that this self-similar thing, the velocity profiles and the temperature profiles are similar to each other. So if there are any obstacles or anything along the path, then the similarity will actually go off, and then you cannot use these correlations directly. You can still use a correlation, but the error you will be getting, you cannot trust how much, like what is the reliability of whatever answers you are getting is something that is questionable. So mathematically, what this would translate to is, once I derive the equations, the entire governing equation, the differential equation, should have only one variable in it, that is eta. It should not have x and y. if after doing all these transformations, if I get a differential equation of that particular form, then the self-similarity is true. So for boundary layer equations, if you people have attempted with minus 1 by 4, and then what happened is the resulting governing whatever equation we get for momentum or energy equation will have x and y terms in it. So the self-similarity is not being preserved with 1 by 4 law, but if you put 1 by 5, then the entire equation, whatever we are going to get, will be independent of x and y, and it will only have eta in each. So the equations are same as before, just that we have redefined Rayleigh number in terms of heat flux instead of temperature difference. And I've written eta as x by delta. It's all the same as before. Psi as alpha times. Again, I've changed the exponent here just to get that self-similarity thing. U is defined as del psi del y. V is minus del psi del x. And T is T naught plus theta times zeta. Previously, this was TW minus T naught or T infinite, whatever it was. So now it will be dt, which is given by this expression. Once you substitute that into the momentum equation, which is u times del v del x plus v times del v del y equal to nu times del v del x square plus g beta t minus t naught, and then do some simplifications. So I just take some terms together, divide with Prandtl number. These are some kind of assignments. Then this is a final equation I will be getting. This equation is not shown in the slides directly, but you can look up any reference textbooks, say by Bijan or Sadek or any other textbook that you can follow. They might use different values here. So instead of this, they will use a different relation where instead of Rayleigh number directly, they'll put RA by 5, or they will use Grashof number, different ways. All that would change is this final equation will have a different form, slightly different from the one that I have shown here, but eventually the solution would be the same. Similarly, you solve for the energy equation. So this would be the equation I'm getting. Now we have to solve this equation using the ND solve just like before. So my governing equations along with the boundary conditions. The boundary condition here, there is one significant change here. So previously when we have the way we define theta, for f everything is same, for velocity everything is the same, but for theta we have defined this as t minus t naught by dt, which is so this is how we are defining theta. So theta at as eta tends to infinite will be 0, because t will be equal to t naught and that will go to 0. But theta at eta equal to 0, previously we know that it is wall temperature, but now I do not know what the wall temperature is. So this is something that we do not know. But what we know for sure is we know theta prime. We can compute theta prime at eta equal to 0, which is basically d theta by d eta, or I'll just do this as k by qw prime delta times del t by del eta. I will write it as del t by del x at x equal to 0 and dx by d eta. Eta is basically x by delta. So d eta by dx is 1 by delta. So this and this will get cancelled. And this particular quantity, k times del t del x at x equal to 0 divided by q1. This particular quantity is minus qw prime by qw prime. So this is coming out to be minus 1. So the boundary condition previously in the initial value problem, like in the constant wall temperature, in the constant wall temperature problem, we know theta at eta equals 0, but we do not know this value. That was what we were trying to find. In constant heat flux problem, we know the theta prime value to be minus 1, and we do not know this. So we are trying to estimate what the wall temperature is. So all I have to do here is while I'm writing here, I have to just put that value here. So I'll assume that, I'll keep theta prime at 0 to be minus 1. And theta, as eta tends to infinite, again I have taken eta to be 10. Beyond that, these values are not changing much. So at 10, it should be equal to 0, and remaining everything remains the same. Here, another assumption I have taken is from the problem itself, that assume Prandtl term to be 1. Otherwise, you have to solve the same equations again and again, like depending on, because these equations, if you see, have Prandtl number in it. The momentum equation has Prandtl number in it. So for each Prandtl number, I'll have a different solutions. So instead of doing that multiple iterations, as I said before, we have to do these iterations again and again. during these iterations for each Prandtl number, I'll have to solve the equation again, get the appropriate heat transfer coefficient into this. So I'm kind of just simplifying it in a way where you only solve the similarity equation once for assuming Prandtl number to be 1. With that assumption, that will slightly simplify. Otherwise, you can also put that, you can also do an iterations in that. So now what we have to do now is the remaining are all the same. You take the air properties, you take the wall temperature as a solution of the differential equation that you have. Substitute eta equal to 0, that will give you the wall temperature. And I mean, since Prandtl number is not changing, this solution is fixed for all the iterations. So my next set of iterations is the properties. I have to change the property values by changing the film temperature. So how I do that is I'll define my root equation, which is TW should be equal to T naught plus QW theta W into this particular value here. So what that essentially translates to is, so I have H of y times TW of y minus T infinite is Q on. So what we are trying to find is TW bar, which you can obtain by and I also know that Q on I can just type this equation. So this will be, I just take 1 by L outside. LL will get cancelled. So I'll have T infinite. Yes. I just need to solve this particular one. So all I have to do is write the equation appropriately. So, okay, instead of writing in terms of H, I have written in terms of K, which is again straightforward. So all you have to do is, you can write this as K times at the wall divided by delta, where this theta W is basically theta evaluated at eta equal to 0. I think I have written a slightly different equation here. Okay, I've taken the direct equation from the top. So you can directly take from here. So T equal to T naught plus theta times delta T. Delta T is theta of eta times delta, where Q all K times delta T by delta. So from this delta T is Q all delta by K. All I have to do is I need wall temperature. So T wall is basically substituting eta equal to 0. That will be T naught plus theta W into QW into delta by K. So if I integrate this to obtain the mean wall temperature, just remove this to remove the confusion. That would give me T naught plus theta W QW by kappa into integral delta dy divided by whatever is the length, just to get the mean value. So this should give me the mean wall temperature. So if you see this relation, so TW is varying as delta, where delta will actually vary as delta by y will vary as RAY to the power minus 1 by 5. So if you substitute this back, so delta will vary as y times RA to the power minus 1 by 5, and RA has some constants G, beta, QW, y to the power 4 by mu alpha kappa whole to the power minus 1 by 5. So if you remove the constant, so delta will actually vary as y to the power, this is minus 4 by 5 and 1 will vary as 1 by 5. So which means TW minus T naught will be varying as y to the power 1 by 5. So if you plot this function, what would happen is y keeps increasing, then it will actually saturate. If this is my y and this is TW minus T naught, so initially it will be 0, it will keep increasing, increasing, and eventually it will become constant. This is how the plot will look like for this particular function. You can take the actual values, plot, and see how this actually looks, which you can do in any tool right now. So this is how I computed the mean wall temperature. So what we are trying to do is solve for this equation. So the equation looks like TW equals to T naught plus whatever I have just written now. And you just solve this equation using find root. So you'll assume an initial value of 90 and then ask it to solve. So I've given accuracy goals are of around 10 power minus 1 and 10 power minus like 10 iterations, and then it eventually converges to around 96. So the wall temperature is close to 96. Once I know the mean temperature, calculating H is straightforward, right? H is basically Q by T mean minus T naught. Similarly, I can calculate the wall temperature at the end of the plate and calculate heat transfer from it. So heat transfer is QW by TW minus T naught, and TW is T naught plus theta times whatever we have, and theta wall times this, the equation that I have just shown before. Again, the mean heat transfer coefficient is higher than the local heat transfer coefficient. Are there any questions? So basically what I have taken down the calculation part from it so that we can focus on discussing on how to approach the problem instead of how to actually do the arithmetic part or solving the differential equation, because most of that is there are tools to actually solve all of that. So we can focus on how to formulate the problem in a way that these tools can actually be used, or what kind of simplifying assumptions we can make and things like that. We can discuss more on that instead of actually solving the problem. If you have any difficulties with this particular mode of solving the problem, we can go back to the standard way of solving with pen and paper. Are there any questions in the problem? Doing these kinds of iterations with hand is actually very tedious, especially when you have property values. Each and every time you have to go back to the table, refer to the properties from the table, like take the linear interpolation, again do the entire steps again and again, which can actually be automated now, like which can actually be programmed easily. Whichever language you're familiar with, attempt them in whatever, say if you're familiar with Python, C, whatever language you're familiar with, try to attempt in your own in that particular programming language, and try to solve the problem, and then we can compare the solutions together. Okay, I think there are no questions in this problem. Then we'll move on to the next one. So the idea of this problem is you have a vertical plate of around 1 meter length, and it is maintained at a constant temperature of 100 degrees Celsius, while the ambient air is at 20 degrees Celsius. So what it asks you is compare free convection heat transfer with that from forcing air over the plate at a velocity equal to the maximum velocity that occurs in the free convection boundary layer. So if you see the velocity profiles that have been drawing lately, the velocity profiles will always look like they will reach a peak and then eventually they will die down. The vertical velocity. So what we are asking now is, let's say this is the peak velocity that is there, Vmax. So instead of doing with natural convection, let's say this is TW, which is constant, and this is let's say T infinite. So what we can do alternately is take the same plate with the same temperature, but then instead of having natural convection, what if we had a forced convection, wherein you will have a constant velocity, so that you will have the boundary layer something like this. And the velocity field is Vmax. I mean, the free stream velocity is equal to Vmax. So the same assumptions, whatever we have, let's say it is 2D study, all those assumptions are there. The question now is you have to compare the heat transfer coefficient here and here. Let's say this is H free and this is H forced. In order to do this, you don't have to do anything. Essentially, it happens naturally. As long as this wall temperature is maintained at that, this convection will always happen. Here, however, in order to maintain this Vmax, you have to externally put, say, pump, fan, blower, whatever, to actually blow the air across, because there will be some finite frictional drop here. In order to overcome, you have to spend some energy here. So which one do you think will be higher? So let's say if I ask H free by H forced. Question is, will it be greater than or less than 1? And why? And whenever you are saying, whenever we are assuming that it is to be forced convection, we are assuming that uh, there is no buoyancy forces acting in this particular case. I mean, otherwise it would be like it wouldn't be a forced convection at all. So like we want the driving force to be way higher than the other forces. That was what we were discussing when we were saying Richardson number is very much greater than 1. You will assume it to be natural convection, and when Richardson number is very much less than 1, you will consider it to be the forced convection case. So which one, like, what do you think? Is greater than 1, less, like which one will be higher, free convection or forced convection? The thing that we are keeping constant is Vmax. Vmax is assumed to be constant in both the scenarios. Which one will be higher? Or how do you go about solving this? Like any approach, strategy, or anything? Okay, let's do it in the brute force way, where we actually solve like take these temperature values, solve the boundary layer equation, get the velocity profile, determine what is the maximum velocity profile, use the correlations that we developed from the forced convection problem before, and estimate the Nusselt heat transfer coefficient from that, and estimate the heat transfer coefficient from free convection, compare both of them. Like that would be the straightforward way. Again, this I've just shown before, so you take the same equations as before. Since the temperature etc. are given, if you substitute those values, you will get the heat transfer coefficient. So the mean heat transfer coefficient I'm getting around 3.84. Once I have the heat transfer coefficient, the next thing is to compute the velocity. So to do that, what I have done is I've taken the solution The solution has two components, f and theta. So from that I'm taking f and I'm calculating f prime, because we know that velocity equation is already there in the velocity equation that I have calculated from minus del psi del x. I'm substituting the value of f prime and all other values that are given to me in the problem. Once I substitute that and put y equals to 1, because it is a 1 meter plate, I'll get my velocity solution. And delta is taken to be 10 times, like because eta equals to 10, I'll substitute that the value here, which is giving me a velocity profile like this, where the peak velocity is around 0.85 and that is happening around 0.0045, whatever the value is. So the peak velocity is around 0.85 meter per second. So this is just a function that does this automatically. So instead of seeing from the plot, you can just put the maximum value of the velocity solution that I have obtained before in the range 0 to x to delta with x as my variable. It will determine the value to be around 0.851 meter per second. Once I have this velocity, what I have to do is use this velocity to compute the heat transfer coefficient if it was a forced convection case. So under forced convection case, the heat transfer, the correlation is 0.664 times Prandtl number to the power 1 by 3 and Reynolds number to the power half, where Reynolds number is b times the length is 1. So I have not written 1 here. Maybe I should just write 1 here. By nu, and that is giving me around 125 point something. So from this Nusselt number, I can calculate my heat transfer coefficient. So that is around 3.58. The one that I obtained from the free convection is around 3.84. If I just take the ratio, I'm getting that to be slightly greater than 1. So what is happening here? So I'm getting the heat transfer coefficient to be higher in case of free convection than when I'm trying to force it under the identical, under similar conditions of wall temperature and etc. This is happening essentially because of the stack, or basically the buoyancy force that is there in case of free convection. So when you have the additional term, the buoyancy force inside that, so that is actually causing you, or maybe once turbulence is explained, then it will be little clear to you. But even under laminar scenarios, because of this buoyancy term that is there inside our governing equations, that is actually enhancing our heat transfer higher than it would be if it were a pure forced convection case. But if obviously the velocity, if you're doing a forced convection, if you put a fan or something, you can obviously increase the velocity to be higher than this one. Let's say the velocity can be say 1.5 meter per second, or higher than that would actually cause noise. But let's say 1 or 1.5 meter per second, then obviously the heat transfer coefficient will be way higher than free convection case. So it depends on your particular problem. So in your particular scenario, if the heat transfer coefficient of around this is sufficient, then you don't have to actually go for post convection. There any questions in this? Okay. Then I have the last problem. So just now I said that there is a point where you have maximum velocity. The question now is, where does this happen? Where does this maximum velocity happen? Let's say this is some delta star or something. So what is this delta star? Or maybe I should ask, what is delta star by delta? That way it will be kind of universal, because this is self-similar. I can say, if I define delta star to be the distance where, or maybe delta star is the distance where v reaches maximum. What is delta star by delta? So that is basically the last question. Since you cannot solve it with hand, because we do not have an analytical solution at this point, all we have to do is again numerically solve the same set of equations, get the velocity profile. Once I have the velocity profile, all I have to do is in this velocity profile, I have one term which is a function of eta and another one which is function of the Rayleigh number and other numbers. So all I have to do is, because there is a negative sign here, I will try to minimize this interpolating function, and that should give me the solution. That is what I have been doing here. So I'm saying minimize that solution, the whatever this function is, and once it tries to minimize, give you that value of eta. So I'm getting the value of eta t, where this is happening to be around 1.30 something. So if I divide that with delta, so that is coming to around 0.13. So around delta star by delta is around 0.13 or so. This is a very rough approximate. You can do it. You can try this your own way in whatever language you are familiar with. Get the solution for eta and then determine where eta is actually causing f prime to be 0. That is your delta. And similarly, find that eta where your f prime is reaching minimum or maximum, whatever it is. That will be your eta star. Determine eta star by eta, and that will give you this. Sorry, eta by eta star, and that will give you delta star by delta. Are there any questions in this? Yeah, I guess there are no questions. And these are the questions I have for this week. If you have any further questions, maybe I'll pause for some time so you can ask. If you do not have any questions, then feel free to leave the session. We'll have the class again next week, Saturday, again 5 to 7 p.m. And please do fill the feedback form that is being circulated through email from the NPTEL team. If you have any queries or concerns, or if you want anything else to be discussed, feel free to write in the feedback form. I'll go through it and accordingly revise whatever is being discussed in these sessions. And have updated the home page, so you can find all the whatever that is being discussed in these sessions from week 7, week 1, like a few of the weeks in between are there on handwritten notes. So I have uploaded them separately on the Google Drive folder that is shared with you. And the remaining slides are there in the website itself. The link for this website is also provided in the Google Drive that is shared with you. So you can go through that particular, like you can go through the lecture, go to that, and then it will be at the bottom of this. You can go through the corresponding week after the session happens. I usually update the questions 1 or 2 days before the, usually 1 day before the class. So if you want to come prepared for the session, you can go through this. I will not upload the solutions, or so you can go through the questions first and then come prepared. And if you have any queries, we can discuss them during the session. Usually I'll update the questions by Friday evening or Friday first or second half. So you can go check it after that. By Friday night, they will be mostly uploaded. Once you can go through the questions before coming to the session, so we can discuss any more queries you have. Okay, then I think that's it. That's from my side. If you do not have any, I think you do not have any further questions. Then I think we can end the session for today. Thank you for joining. We'll again meet next week.